Yeah, so in the previous section, we just loaded the weights from OpenAI into our GPT model architecture. And now we are going to get this GPT model architecture ready for the classification fine-tuning. So before I go to the code, just to conceptually showing you what's going on or what's going to happen. So here, what we are doing is we are looking at the GPT model architecture that we coded in chapter 4 and then pre-trained in chapter 5, and where we just loaded the pre-trained weights into this architecture. Now what we are going to do is we are going to replace this massive output layer that goes from 768 to 50,257 dimensions by a smaller output layer. So why do we have this massive output layer again in the first place? So we do have this token embedding layer that goes from 50,257 potential token IDs into an embedding space. So we carry out the through these embeddings. We have embeddings of size 768, where this number comes from the fact that we have 768 dimensions in the as embedding size in the smallest model. If you're using one of the bigger models, you might even have bigger embedding dimensions. But yeah, we are working with a small model, so our embedding dimension is 768. That's where this number comes from. And so in the output layer, we have to go back into the vocabulary space. So because ultimately we want the token IDs. So we go from 768 back into the 50,257 dimensions from our tokenizer. And like I said before, we don't actually need that many words if we just want to classify something as ham or spam. So for that, ham and spam, there are two words. So we need actually only two tokens, two potential output tokens. So we can go ahead and replace this massive output layer with this smaller output layer where we have, again, still the same embedding size because, we don't really change anything inside the network, but then we only need two potential words, ham or spam. So we replace this by these two output nodes. And in general, we can say that the number of classes is equal to the output nodes. A curious reader might note, for example, you might know from classic machine learning or deep learning that for a binary classification task, so a classification task where we have two classes, you technically only need one output node. But to keep the code in this notebook here more general, we will be using two output nodes for our two classes so that we can say the number of output nodes is equal to the number of classes in the data set. So for example, if you have another task, so this would work also for any type of task. If you have, for example, a task where you want to classify newspaper articles, so you might have business news, sports news, politics, and finance. So you have 4 different types of articles. You would then have 4 output nodes. So you can change this based on your task. But yeah, since we only have 2 output classes or 2 classes, we have 2 output nodes. So let's go ahead and make these model changes I just described. So first, never a bad idea to just make sure the model is loaded correctly. So we are looking at this model here. Like I mentioned, we have the 50,257 to 768 embedding. And then, we are scrolling through the different transformer blocks. So we have, 12 transformer blocks. So up to here, that's a 12th transformer block. And then we look at the output layer. And this is the layer we want to replace by our smaller layer. So before I do the actual replacement, I want to make one more note. And so pre-trained models are actually pretty good at, extracting information from the input text. So this whole network has been trained, to do something useful in the pre-training task. So we don't really need to modify anything here. We can actually just replace this layer and just fine-tune this output layer. And I do have an article on that. It's a pretty long time ago, but where I analyzed like the trade-offs of training different layers. So let me just see if I can find it here. Fine-tuning large language models. And so it's a different architecture and it's a different data set. So let me see. So it is a different model and a different data set than we are working with, but it's, I would say, a trend that generalizes in certain aspects, where what I'm trying to tell you here is kind of like transferable to our model and our data set. So what we are looking at here is the classification accuracy. It's on a different data set, but it's similar. I mean, in that sense that we are classifying two classes, and that's the accuracy here. And there are 3 bars. There's the test accuracy, the validation accuracy, and the training accuracy. For, keeping this discussion brief, let's just focus on the training accuracy, the first bar. And this accuracy is achieved if we train only the last layer. So the last layer means this one here. Now, if we train the last 2 layers and the last transformer block, so let's say this corresponds to like these 2 and then the transformer block. If we train this part, we get better accuracy. So we train more things. We get from, I would say, 76% to 87.5%. Now, if I train even more, like the 2 last transformer blocks, so if I train this whole part here. Oh, sorry, what happened? One moment, I somehow pressed some wrong button on my keyboard. Okay, so if I, up to here, if I train this whole part here, we see we get even better performance. Now we have something maybe around, I don't know, like 90%. And yeah, so the more we train, it seems like the better the accuracy. But then we hit a point where we have diminishing returns. So you can see here, there's not much improvement really. I mean, we still keep it around 90% here. And moreover, also when we look at the training time, how long it takes for the fine tuning, here we are around, I would say, what is it, like 2.5 minutes or something, if we only train the last layer. If we train the last layer and the last transformer block, it's about the same. Training 2 transformer blocks, yeah, it's a bit slower, 3.5 minutes. But then if we train the whole model here, all the layers, yeah, we see it's 7 minutes. It's almost like 2 to 3 times what it takes here to train only the last layer, or the last 2 layers. But it's not that much better. So we spend, especially in this range, more time training, even though we don't really get any returns. And so this is generally true. The simpler the data set, the more this applies essentially, because for a small, simple data set, it's kind of overkill to train everything. In fact, the more we train, typically the more data we need to avoid overfitting. And so if we have a small, simple problem like the spam classification problem, it's not really necessary to train this whole model. So we can get away with only, for example, training the last layer, the layer norm here maybe, and the last transformer block. So long story short, before I go ahead and replace this layer with the smaller layer that I mentioned here, let's actually go ahead and make the model non-trainable. So in order to do that, we can freeze the weights. So what we can do is, for example, we can iterate through the model parameters. So for each parameter, so that would be a weight tensor or bias tensor in the model, we set the requires gradient argument to false, which then means this weight tensor or bias tensor won't be trained when we are training the model. So we are freezing the model. So this means essentially, another word for that is freezing the model or the model parameters. So they won't be updated during the training. And now we can go ahead and replace the output head. So what we go here is output head. And so we will replace this. So this one will be trainable because we initialize it with new random weights, and by default they are trainable. So we are going to use 768. So to make this a bit more general, let me go ahead here and copy this name. So we can add the embedding dimension as a configuration here. So it will also work in case you choose to fine tune a larger model. So embed dim. And then let's define the number of classes to 2. And then we can say num classes. And then also let's set a random seed because we are initializing it here with random weights. Okay, so now we should have a new output layer. So you can see now the output layer is improved. Sorry, not improved, replaced. And now, yeah, this would be what I just showed you. One thing is, according to this, training the last transformer block is not a bad idea. Maybe the 2 last transformer blocks, that's maybe a reader exercise for you. But I would say we should probably train this last transformer block at least. So what we are going to do is, I don't need to scroll that much. So what we are going to do is, this is already unfrozen. We are also going to unfreeze this one and this one. So unfreezing means making it trainable, basically. So first we made everything untrainable, only this is trainable. Now we make these things also trainable. And why this last layer norm? I mean, well, you don't have to, but I feel like it's natural or more natural when we make this trainable and we make this trainable to also make things in between trainable. Otherwise, it would be a bit awkward. So what we are doing now is we are making this transformer block here trainable by setting this again to true. So this would be the last transformer block in our model. And then the final layer norm. So this layer norm, we will also make that trainable. And so now, only the output head, the final layer norm, and the final transformer block will be trainable. Before I end this session, I wanted to show you one more thing. And so what happens when we give it some input now after our modification? So let's just assume we have some simple input here. And so this input is 4 input tokens corresponding to, let's say, a text message, someone asking us, do you have time? Here, again, I just add the batch dimension like I usually did. So because our model expects input batches, because without that, this would be a torch size of just 4. But our model expects batches during training and everything. And so let's say our model receives this input. So when we do torch.noGrad, the context, and then let's say, outputs model inputs. So if we get that, so let's see how outputs looks like. So you can see it's now, again, still 4 rows, right? Each row corresponds to each token ID or token input here. But now we only have 2 output dimensions. Before, in chapter 5, we looked at this massive outputs tensor because before we had 50,256 output dimensions. Now, as expected, we only have these 2 output dimensions. In particular, we are also, by the way, only interested in fine-tuning the last position. So here, what we are looking at is the last token. We will talk more about this, but so technically we are only considering this last token here. So this one, we are going to not fine-tune anything related to those tokens. And the reason is that the last token contains the information about all the other tokens. So so here's just like a figure showing you what we just did. If we have some input text, we get this tensor, and then we only focus on the last row corresponding to the last token. And the reason is it's due to the attention mechanism. So if you remember, it's been a long time, but from chapter 3, how attention works, we have this causal mask. So if you consider these rows as the input, so when you look at the first input position, do, the self-attention is only between do and do itself. And then if we have these do you, so the word you, the context vector for that one, contains information about do and you. So we have attention weights for do and you. But it can't look into the future because of this causal attention mask. So it can only always look to its current position, right? And so if we consider this token here and we make our decision, so maybe going one step back. So our task is, based on these numbers, to classify whether something is spam or not spam. So we could look at this whole thing. We could look only at the first row or the second row. But the most efficient way to do that is to look at the last row and use these numbers to determine whether the input is spam or ham, because this one contains information about everything else. So going here again, the last token, do you have time, it has information about all the other tokens. So the context vector has all the information because we have the attention weights for that. And so the model, when we fine tune it, will learn how to use these attention weights effectively for making the decision whether something is spam or ham. And so that is why we only need to focus on the last position here. But yeah, this is what we are going to do. So we are going to next fine tune the model to do this classification task. And I think, yeah, this will maybe then also make things a bit more clear. And yeah, and so with that, we have modified the architecture, and we will just in a few moments fine tune it.
Get this book at manning.com.